Today we're going to be going over Laplace transforms and transfer functions. Alright, the very first thing we're going to start off with is the definition of a Laplace transform. If you've taken late before, this might look pretty familiar to you. The Laplace transform denoted capital F, in this case, of S, or the Laplace of lowercase f of t is equal to the integral from negative infinity to infinity of e to the negative s t, in this case, f of t dt. Keep in mind here that if there's a unit step, as we learned in Leipzig, it's going to actually start from 0, or it might start from a different value. It might go up to a different value, but this is the basic standard definition. We're going to go ahead and also make a Laplace table. This is really good to take into exams. So the first function that we have here is just your basic unit step of t. The Laplace transform of it is 1 over s, and then the region of convergence, and we'll go into more detail about this later, is when the real value of s is greater than 0. Right, the next one that we have is e to the at us of t, and then this turns into 1 over s minus a, and then it converges when the real part of s is greater than a. Let me just move this up a little bit. The next value that we have is e to the at us of negative t this time. If you remember this from Leipzig, it's called anti-causal, and we'll go into more detail about that later as well. The Laplace transform is negative 1 over s minus a. The real value of s, since it's anti-causal, is when it's less than a. Sorry, the ROC is when the real value of s is less than a. Then we have cosine of omega t with our unit step of t, and then that becomes s over omega squared plus s squared, and it converges when the real part of s is greater than 0. Then we have sine of omega t, and we can't forget our unit step, which becomes omega over omega squared plus s squared, and it also converges when the real value of s is greater than 0. We also have our impulse here, delta of t, and the Laplace transform of that is just 1. It converges on all values of s on the complex plane. Finally, there's one more, and this is a bit of a property, but it's just good to have here. T to the n, e to the a, t, us of t. The Laplace transform of that is n factorial over s minus a to the n plus 1. And the ROC does not change based on that. So it's the same ROC as you would have up here, where it's the real of s is greater than a. Cool. The next thing we're going to do is go through the Laplace properties. So the first thing is that they are linear. a1 f1 of t plus a2 f2 of t becomes, we do the Laplace, a1 capital S f of s plus a2 capital F of s. So catch here that I am capitalizing the f, and then instead of a function of t, it's now a function of s. We also have a shift here where f of t minus tau becomes e to the negative s tau times of s, so you just kind of add or multiply by that e. Then I forgot to mention here the region of convergence for when you're adding multiples of different Laplace transforms is the intersection. So ROC1 intersects with ROC2, and then for that shift, it does not change. So we'll just put the same. Okay, and now if there's an e to the negative at in your original function, so if it's that times the function, then the Laplace gives you f of s plus a. So you're replacing all your s's with s plus a's. In this case, your ROC shifts by negative a. The next one that we have here is f of at. So if all your f of t's have a multiple for the t, take the Laplace of that, it becomes 1 over the absolute value of a times f of s over a. And here, the ROC is a little bit complex. If f of s originally has an ROC that's causal and greater than theta, then the ROC is now, when the real of s is greater than a theta. And then if it's anticausal, so I'll just put if real of s less than theta, ROC is now real of s less than a theta. The next property here is if you have a t to some exponent times f of t, you take the Laplace of that, it'll become negative 1 to that exponent times the nth derivative of your f of s. And the ROC does not change. Okay, I'm going to move this down a little bit because I didn't allow enough space. All right. If we have some derivative of a function, so fn of t, that'll become s to the n, capital F of s, and you'll use this one a lot in your homework and in future problems. And then again, the ROC does not change. And then finally, this should look familiar from Lenzig. If you convolve f with g and take the Laplace, it's actually just multiplication in the Laplace domain, which makes calculations a lot nicer. And again here, the ROC is the intersection of ROC1 and ROC2. Cool. So what is this ROC? The ROC is where the function converges, essentially where it does not go to infinity. If you take your average transfer function, and this again should look familiar from Lenzig, we remember that h of s is equal to y of s over u of s. So to calculate the zeros of the transfer function, you're going to set y of s equal to 0, and to calculate the poles, you're going to set u of s equal to 0. You can just solve for that as you normally would. It typically involves some factoring, and that's that. We can also take a look at the properties of the region of convergence. Let's say we calculate our poles, and we get a pole at positive 2. And it does not matter what the imaginary part of that pole is. As long as the real part is 2, we're good. So it could be 2, or it could be 2 plus or minus I, or something else along those lines. Either way, we're just looking for the value that we put on the x-axis, which is the real part. So if we have 2, then we would draw our line at 2, and if the function is causal, then our ROC is going to be to the right of 2. If instead it's anti-causal, it's going to be to the left of 2. But let's say we calculate another pole, and we actually got 2 poles, and the other pole here is at, what is that, maybe -1.5. So again, we have causal if it's to the side, anti-causal if it's to the left of the leftmost pole. Then we actually have something called non-causal if it's between 2 poles. And what this would look like is something that is causal with respect to the left pole and anti-causal with respect to the right pole, and that makes it non-causal. The other one the other property that you're gonna get asked about is Beebo stability. There are a bunch of different definitions of this, and there's a really mathematical, intense way to calculate it. But for the sake of your exam, it's gonna be Beebo stable if it includes the imaginary axis. So I'll give you some examples. If we have a pole at, let's call this -2, and let's say it goes to the right of -2, then remember this is causal because it's to the right, and it's Beebo stable because it includes this imaginary axis. However, if we were anti-causal and we were going to the left, it would not include the imaginary axis, it would not be Beebo stable. This is a trick I've noticed that they try to pull on some of the exams and maybe the homeworks. If you have a pole here at 0, it can never be Beebo stable with respect to that pole because the poles are never included in the ROC. So as a result, since 0 can never work, 0 is not part of the ROC, it's always going to be unstable if you have a pole at 0. When you're calculating all these on different exams and on your homework, there are a few math tricks that Dr. Sarma goes over that are really helpful. So I'll just review those briefly here. There's a way to do partial fraction decomposition that does not involve as much intimidating algebra, perhaps. So we'll go over that here. So if we have s plus 5 over s squared plus 5s plus 6, we can factor the denominator into s plus 2, s plus 3. But now we want to break it up so we can do a Laplace transform on this. And the way we would do that, if you remember from last time you learned partial fraction decomposition, you have an a over s plus 2 plus a b over s plus 3. And the way that Dr. Sarma showed us to do it is it's called the cover-up method. So here we see that to get our a happens when we covered this up, we covered the s plus 2 up. And to be able to do that, we have an s of -2. So when we have an s of -2, the numerator here is going to be -2 plus 5, and the denominator is -2 plus 3. So this becomes 3 over 1. So our a is actually equal to 3. And then to find our b, we pull a similar stunt with the s plus 3. So if we call our s -3, right, because -3 plus 3 equals 0, then we end up with, on top, -3 plus 5, on the bottom, -3 plus 2, and this comes out to +2 over -1, or just -2 for a b. And that is an easier way of doing partial fraction decomposition. Just for practice, let's take this now and let's do a Laplace transform on it. Sorry, an inverse Laplace transform on it. We see that this has s's, so it's in the Laplace domain. If we refer back to our Laplace table, we see here that 1 over s minus a is e to the a unit step of t. In our first one, we're multiplying by 3, so we're going to do 3 times, and then it's s minus a. In this case, our a is -2 because s minus -2 is the same thing as s plus 2. So we're going to have e to the -2 t us of t, and then we're going to repeat the process for the next one, -2, because that's our constant that we're multiplying by. E, in this case, -3t us of t. Cool. Then the other math trick, and this was new to me, is if the powers of your numerator and denominator are the same, you cannot use a partial fraction decomposition. PFD only works if the denominator's degree is greater. Instead, what we can do for this is essentially add 0. We're going to add 0 by adding 1, so we can have it cross out with the denominator. I'll show you what I mean here. So we have our s plus 2. We want to make it an s plus 3 so it matches the denominator down here. We do s plus 2 plus 1, then since we added 1, we also have to subtract 1 over s plus 3. And that comes out to s plus 3 minus 1 over s plus 3, which we can then break into s plus 3 over s plus 3 minus 1 over s plus 3, which is also equal to 1 minus 1 over s plus 3. And this will be very helpful once we start doing block diagrams later on. That covers everything for the first video of systems and controls. Thanks for watching.